All right, let's dive right in. Today, we're tackling a classic Class 12 physics experiment, getting to know the unique personality of a p-n junction diode. We're going to break down exactly how you can read its performance report.
But first, let me ask you something. What do you think is the most important one-way street in the entire world? You're probably thinking of some massive highway or a busy street in a big city, right?
Well, the answer is way, way smaller than you think. In fact, there are probably billions of them inside the very device you're using to watch this right now. So let's zoom in. We're talking about these tiny, microscopic one-way streets. They're kind of the unsung heroes of all our modern gadgets. I mean, these are the things that take the AC power from your wall and turn it into the DC power that charges your phone.
And this is the little guy we're talking about, the p-n junction diode. At its heart, it's a really simple idea. It's made by squishing together two types of materials, a p-type and an n-type. And this creates a device that acts like a perfect little gatekeeper for electricity, letting it flow one way, but slamming the door shut if it tries to go the other way. So, our mission today is to get to know this gatekeeper a little better. And how do we do that? Well, we put it to the test. We're going to create its performance report card. And that report card is called the IV characteristic curve.
But to get the full picture, you can't just test it in one situation. We need to see how it acts under two totally different conditions, forward bias and reverse bias. Think of it like a comprehensive stress test. And here's the key thing to remember. The IV curve isn't just some dry, boring graph. It's literally the diode's personality test. By applying different voltages, that's the V, and measuring the current that flows, that's the I, we can map out its entire character. All right, let's start with the first test, forward bias. This is where we're going to try and get that gate to swing open and let the current flow right on through. So to put a diode in forward bias, here's what you do. You connect the positive side of your battery to the P side of the diode and the negative side of the battery to the N side. This is basically the on switch. This setup is designed to let a flood of current pass right through. Now, what's really cool about this whole procedure is the story it tells. You see, you start off with good, clean connections. That's just good science. Then you start slowly turning up the voltage. At first, like step 3 says, you apply a tiny bit of voltage and nothing. The current is basically zero. It's like you're pushing on this gate, but it's just not budging. But then, and this is the awesome part, as you get to step 5 and you hit this magic number called the cut-in voltage, it's around 0.7 volts for a silicon diode, bam! The floodgates just burst open. The current suddenly surges. That's the exact moment we're trying to capture. And this table, this is basically your lab notebook where you're writing down that story. You're carefully recording every little voltage step and what happens to the current. You're not just collecting a bunch of numbers here. You're pinpointing that exact moment the diode wakes up. Okay, so we've seen how to open the gate, but that's only half the story, right? Now we're going to flip the script and do the reverse bias test. This time, our goal isn't to open the gate. It's to see just how well it can stay shut. For reverse bias, it's super simple. You just do the exact opposite. You connect the positive terminal to the N side and the negative terminal to the P side. This is the off switch. Now, the diode should act like a roadblock, stopping almost all current from getting through. Now, the procedure here is pretty similar, but whoa, the results are completely different. As you increase the voltage this time, you'll only see a tiny, tiny trickle of current. It's called leakage current, and it's so small you have to measure it in microamps. The diode is holding strong. But, every gate has its breaking point, and if you push it too hard, you're going to find it. You keep upping the reverse voltage until you hit what's called the breakdown voltage, and all of a sudden the gate just shatters and a huge current rushes through. You have to be super quick to turn it off or you'll damage the diode. So let's put these two personalities right next to each other. On one hand, you've got forward bias, P to positive, N to negative. The resistance drops way down and current flows like a river. On the other hand, you have reverse bias. Flip the connections, the resistance skyrockets, and the path is blocked. See? It's the perfect one-way street. All right, time for the big reveal. We've got our data from both tests, opening the gate and then trying to break it. Now we put it all together on one single graph. And this graph tells the diode's entire story in one beautiful picture. In the forward bias area, you see pretty much nothing, and then whoosh, an exponential explosion of current right after that threshold voltage. Then in the reverse bias area, it's just a flat line, almost zero current, holding on until, bam, that sharp drop at the breakdown voltage.
This graph right here, that's the diode's signature. It's its fingerprint.
Okay, so you get the theory. That's great. But how do you actually nail this experiment, especially when your teacher or an examiner is watching over your shoulder? Let's talk strategy.
First up, precautions. And look, these aren't just suggestions, they are absolutely critical. Loose connections will totally mess up your readings. Leaving the circuit on just heats everything up, which can change your results. And most importantly, you have to respect that breakdown voltage. Pushing past that point is a surefire way to fry your diode for good. You don't want to do that.
And you've got to be aware of what can go wrong, right? I mean, sometimes you just get a faulty component. It happens. But more often than not, it's a simple mistake, like hooking up the battery backwards. That'll throw everything off. So just double check your setup before you start. Seriously, in the lab, attention to detail is your best friend.
So there you have it. We've cracked the code on the diode. We know its one-way personality, we know its trigger point, and we know its breaking point. This little component is a huge building block for everything. So it makes you wonder, right? What other stories are out there, hiding inside transistors or capacitors? The lab is just full of these personalities. Now go find them.